So we'll look at some PV diagram problems. Here we have 1.0 moles of an ideal monatomic gas occupies 3 liters at a pressure of 1.2 times 10 to the 6 pascals. It expands isobarically to 6.0 liters. So draw this on a PV diagram. And so to draw it on a PV diagram, we just draw a pressure versus volume graph. Right? And we're going to put the pressure here, so we'll call this P1. And P1 is this guy, 1.2 times 10 to the 6 pascals, right? And we'll call this the volume it starts at, V1, and that's going to be 3 liters. And so it's going to expand to 6 liters, and so that's going to be about double that. And so that's V2 and V1, right? This is N, the number of moles. And so I start here, right? And I go over to here. And so I would say that's drawing that on a PV diagram. And so part B is going to say determine P, V, and T at both points. In other words, here and here, right? And so we'll call this 1 and we'll call this 2. And then we can say, well, we're going to make a little table with P and V and T. And then 1 and 2, right? And we're just going to fill out our table here. And so, so right away we know that V1, we'll put this in liters for now, and we'll put this in pascals, and this in Kelvin, right? And so the pressure is 1.2 times 10 to the 6th, that's P1, right? And turns out that P2 is also 1.2 times 10 to the 6 because it's an isobaric process, right? And then V1 is 3 liters, and I don't have to put a liters there because they're at the top of the table. And V2 is 6 liters. And then I have to determine the temperatures, right? Well, the temperature, T1, is I can just use the ideal gas law. It's P1 V1 over NR, right? And that's 1.2 times 10 to the 6 pascals times 3 times 10 to the minus 3 liters. It's important to get the units right on these things. Oh, times 10 to the minus 3. After having said that, I got it wrong. Meters cubed, right? I've got to get this in SI units. I don't have to use SI units, but if I do, I want to be consistent, right? And so then it's 1.0 moles times 8.314 joules per mole Kelvin, right? And so that's this is 3.6 times 10 to the 3rd divided by 8.314, which is T1 is 433 Kelvin. So that's a large number, but okay, it is what it is. And so that's this guy. Sorry. 433 Kelvin, right? And now we want to figure out this guy, and we have a few ways to do that. We can use the ideal gas law and just say T2 equals P2 V2 over NR. Hopefully you can see that that the only thing that would change in this equation for T2, right? T2 is equal to P2 V2 over NR. N won't change, R won't change, and the pressure doesn't change. It's just the volume changes, right? And the volume is twice as big, and so this is going to be 866 Kelvin. Right? And so that gives me the pressure, the volume, and the temperature for both of these 2 points. Okay, the next part of this we're going to do is we're going to calculate, we're going to use the first law of thermodynamics to determine the change in internal energy and the heat added and the work done for this process going from 1 to 2. So same problem, and now we're going to determine the change in internal energy, Qn, and work by for this process. Remember, we've already determined PV and T for, if you look at the table on the previous screen, for these processes. And so if you recall, the first law of thermodynamics is just conservation of energy, which says the change in internal energy is equal to Qn minus the work by, right? And so we've got some formulas for each of these things. The change in internal energy is just, we've already said CV delta T, which is 3/2 because it's monatomic, right? Times N times R times delta T, delta T, which is 3/2 times 1.0 moles times 8.314 joules per mole Kelvin times, we said about 860, I rounded a little bit, minus 430 Kelvin. Right? And if you evaluate that, you get about 5,360 joules. So that's the change in the internal energy. The work by is just equal to the integral of the pressure d volume, right? But in an isobaric process, this is just the pressure times the integral of dV, because the pressure is constant through the whole thing. It was a horizontal line on a PV diagram, right? In fact, when we drew it on a PV diagram, it looked like this. And so I think I've said this before, the work done is just the area under this curve. That's what happens when you integrate from here to here in PdV. You're just calculating, just like any integral, you're calculating the area under the curve. And so since it's a horizontal line, this is just P times delta V, which is just 1.2 times 10 to the 6 pascals times the change in volume, which is 6 times 10 to the minus 3 meters cubed, minus 3 times 10 to the minus 3 meters cubed. Right. And when I evaluate that, that just ends up being 3,600 joules. And so that's the work by. And so now we can use this formula to say Qn is equal to the change in E internal plus the work by. Right? It's 3560 plus 3600, which comes out to roughly 8960 joules, something like that. But we can actually check this because we have a formula for Qn for a constant pressure process. It's Cp delta T, which is 5/2 nR delta T. The 5/2 comes from the fact that Cp is nR greater than Cv, and Cv for a monatomic is 3/2 nR, and so Cp is 5/2 nR. And so this becomes 5/2 times 1 mole times 8.314 joules per mole Kelvin times the temperature difference, which is 860 minus 430, or about 430. I rounded that a little bit, but. And so if you multiply this out, I think you get 8940 joules or something like that, which was within rounding of the answer we got by energy conservation. So they're all consistent. And so this describes the first law of thermodynamics for the process of going from position 1 to position 2 as described on here. And this is for an isobaric process. Right, and so we'll look at some other processes also. So in this problem, 1.0 moles of an ideal monatomic gas occupies 3 liters at a pressure of 1.2 times 10 to the 6 pascals. It expands isothermally to a volume of 6 liters. In other words, it doubles its volume. So draw this on a PV diagram. And so let's put a PV diagram over here, right? And so here's pressure, and here's volume. And so we'll call this the starting point, let me draw it out here a little bit. And so this is V1. That's what we're calling V1, right? And it expands to twice that, so we'll call this V2. And so this is P1, and this is P2, and it does something like that, right? There's position 2, there's position 1. That's what isothermal lines look like, and we'll talk about why we know that here in a second. And so part B is determine P, V, and T for both points. And so we'll just make a little diagram. Pressure in pascals, volume in meters cubed, and temperature in Kelvin, right? And this is for state 1 and state 2. We'll make a little table here, bing, bing. There we go. All right. And now we're going to say, well, we know this guy. This is 1.2 times 10 to the 6th pascals. We know this is 3 times 10 to the minus 3, and this is 6 times 10 to the minus 3. And that's all we know. And so if we want to calculate T1, we can say P1 V1, that's these two guys, equals NR T1, or T1 is equal to P1 V1 over NR, which is equal to 1.2 times 10 to the 6 pascals times 3 times 10 to the minus 3 liters over 1.0 moles times 8.314 joules per mole Kelvin. Right. And if I do that on my calculator, that's 3.6 times 10 to the third divided by 8.314, which is about 430 Kelvin. So this is 430 Kelvin, and that means this guy is also 430 Kelvin because we said it expanded isothermally, right? And so now we can use just the proportionality rules for this, right? P1 V1 over T1 is equal to NR, and that's equal to P2 V2 over T2. Since the number of moles doesn't change, I can do this at either point, and that means these two are equal. And since they have the same temperature, I can say P1 V1 is equal to P2 V2. And since V2 has twice the volume of V1, that means P2 has to have half the pressure of P1. So P2 is equal to P1 V1 over V2. And since this is 3 liters and this is 6 liters, I'm just getting P1 over 2, or 6 times 10 to the 5th pascals. The thing to notice about isothermal lines, right, is that if I write PV equals nRT, then for an isothermal line, P I can write as nRT over V. And this is the functional behavior of the pressure in a PV diagram for an isotherm. Remember, for an isothermal line, T doesn't change. And so this numerator is constant. And so P goes as 1 over V. That's why the curves always look like this. They look like hyperbolas. Isothermal lines do, because P varies as 1 over V. So on the next page, we're going to do conservation of energy for this. We're going to calculate the change in internal energy. The first law of thermodynamics. We're going to calculate the change in thermal energy for this process, Qn for this process, and the work by the gas in this process. So now we're going to determine the change in internal energy, the heat added, and the work done by the gas for this process, remembering that the that the first law of thermodynamics says the change in internal energy for a process is equal to Qn minus the work by, right? And if you remember, for any process, the change in internal energy is equal to the heat capacity at constant volume times the temperature change. But since this is an isothermal process, the temperature change is just 0. Right? There's no change in internal energy for something that occurs at constant temperature. Right? And so now we can calculate the work by, right? And the work by is equal to the integral of P dV. And we've already said that we can use P is equal to nRT over V because then when we put that as an integrand in this equation, the only thing that varies is V, and it gives us an integral in terms of V. This becomes work by is equal to nRT. These are all constant times the integral of dV over V. Again, isothermal process, temperature doesn't change, right? And so that's just nRT times the log of V, except evaluated at 1 and 2, right? The limits for this integral are positions 1 and 2. And so that means that the work by is equal to nRT times the log of V2, which is 6 times 10 to the minus 3 cubic meters, minus the log of V1, which is 3 times 10 to the minus 3 cubic meters. And so that's, if I write that out, that's equal to nRT times the log of the ratio, right? Log of A minus log B is log of A over B. Well, this is just the log of, I guess I'll write it all out, 6 times 10 to the minus 3 meters cubed over 3 times 10 to the minus 3 meters cubed, right? Which is just 2, right? And so this is 1.0 moles times 8.314 joules per mole Kelvin times the temperature, which is 430 Kelvin, times the log of 2. And so for that I get the work by is 2480. And so since E equals 0, this implies that Qn is equal to the work by, because up here, if this guy is 0, that means these two guys are equal to each other, right? And so Qn equals work by equals 2,480 joules. In other words, in the process where the gas moves from this position to this position, heat is being absorbed, and that as the heat is being absorbed, it's doing the work of expanding the volume. And so the total internal energy stays the same because work is being done by the gas as the heat is being absorbed by the gas, and the total internal energy of the gas does not change. That's an isothermal process. So in this case, we're going to look at an adiabatic process, and we're going to say 1 mole of an ideal gas at 1.2 times 10 to the 6 pascals occupies 3 liters. The gas expands adiabatically this time to 6.0 liters, and the first thing is to draw this on a free body diagram. Just loosely, it looks like this. Here's my pressure. Here's V1, and twice that is V2, and so I'll call V1 and V2. P1 will start up here, say P1. And similar to an adiabatic curve, similar to an isothermal curve, an adiabatic curve drops like this. And so that's my result. Again, you know, the work by the gas is the area under the curve each time. And so that's the work by. We're going to get to that at some point here. So the first thing they're going to ask us for after the drawing is determine P, V, and T at both points. That is to say, point 1 and point 2. Right, and so we'll just make a diagram over here. The pressure in pascals, the volume in cubic meters, and the temperature in Kelvin for positions 1 and 2, and I can just draw those out like that, right? And so I know that V1 is 3 times 10 to the minus 3 liters, and V2 is 6 times 10 to the minus 3. Sorry, those are in meters cubed. I don't need a unit there. Right, this guy I already said is 1.2 times 10 to the 6th, and that's what we have, right? And so we can right away determine T1, this guy, right? T1 is equal to P1 V1 over NR, and we've done this enough times. This is 1.2 times 10 to the 6th pascals times 3 times 10 to the minus 3 meters cubed over 1.0 liters times 8.314 joules per mole Kelvin, right? And that gives me about 430 Kelvin, so that gives me a 430 Kelvin. And now we've got to determine these guys. I have two unknowns here in this guy, and so I can't just use the ideal gas law. In the isothermal part, I know that this temperature is the same as this temperature, right? In an isobaric situation, I know that this pressure is the same as this pressure. The tool we have in an adiabatic case is that for adiabatic processes, we showed that TV to the gamma minus 1 is a constant. And so that means, you know, T1 V1 to the gamma minus 1 equals T2 V2 to the gamma minus 1. If you remember, gamma here is CP over CV. And so for monatomic gases, CP is equal to 5 halves NR, and CV is equal to 3 halves NR. For diatomics that are rigid, you know, not able to vibrate, this is 5 halves and that's 7 halves. This one, CP, is always 1 unit NR greater than this one. And so this means that gamma is CP over CV is 5/3. That divided by that is 5/3. And so what this means is T1 V1 to the gamma minus 1 equals T2 V2 to the gamma minus 1. And that allows me to have 3 knowns, T1, V1, and V2, and 1 unknown. So that tells me that T2 is equal to T1 V1 to the gamma minus 1 over V2 to the gamma minus 1. And that's T1 times V1 over V2 to the gamma minus 1. I'm going to have to erase this a little bit, right? And that's equal to 430 Kelvin times, so V1 over V2 is just that divided by that is 1/2, right? 3 times 10 to the minus 3 over 6 times 10 to the minus 3 is 1/2. And this is 5/3 minus 1. And so this is 430 Kelvin times 1/2 to the 2/3 power. What I get for that is 3.74 times 10 to the 5th pascals. Nope, didn't do that right, sorry. got the wrong number there. If I evaluate this, I get 270 Kelvin. I just got ahead of myself. That's 270 Kelvin. You can check my math. And this is the thing, it's 3.74, but we get to this guy. Now that we've got these two, I can just use the ideal gas law. There are a lot of ways I can get this guy. There's an adiabatic rule for this one also, but I can just as easily say P2 is equal to nRT2 over V2, and that's equal to 1.0 moles times 8.314 joules per mole Kelvin times 270 Kelvin over 6 times 10 to the minus 3 meters cubed, which is 3.74 times 10 to the 5th pascals. And that's what I was trying to write over here a second ago, 3.7 times 10 to the 5th pascals. And so that gives me the pressure, the volume, and the temperature at each point. And in the next part, we're going to determine the change in internal energy, Qn, and work by, right? And you should already see that for an adiabatic process, Qn equals 0, because that's the definition of an adiabatic process, is there's no heat transferred. And so we'll do those on the next screen. So I've moved the table over here. This is the table we calculated in the last part with the pressure and the volume for this adiabatic process that looked like this, right? Here's P and V, and so we have three adiabatic rules here. We have P V to the gamma equals constant. The one we used was T V to the gamma minus 1 equals constant. We use that to get the temperature, but you can also rearrange this using the ideal gas law and get a pressure-temperature relationship, which is P to the 1 minus gamma times T to the gamma equals constant. But if you grab this one, you get P is equal to some constant over V to the gamma, and that's what tells you that this looks like this. In our case, gamma for a monatomic gas is 5/3, and so it's not quite proportional to 1 over volume, which it is for an isothermic. It's a little steeper drop than that. And so if you see graphs of them together, you might see if we drew the isothermal graph from the previous problem, it would be up here a little higher like that, and this one would drop down a little more because it's a larger exponent for the adiabatic curve. But anyway, the part of calculating these guys is straightforward. Qn equals 0 because it's adiabatic. And that's the definition of adiabatic. And so that means we're just left with calculating these two. And we could try to integrate that, but we can just as easily say the change in E internal, or more easily, is equal to CV delta T, which is 3/2 nR delta T, which is 3/2 times 1.0 moles times 8.314 joules per mole Kelvin times 270 Kelvin. I'm a little out of room here. Minus 430 Kelvin. Right? It's the final temperature minus the initial temperature because we went this way. Right? And so what I get for that is about minus 2,000 joules. Right? And since the change in internal energy equals Qn minus work by, then minus work by is equal to minus 2,000 joules, or work by is equal to 2,000 joules, which is what it should be a positive number, right? Because the gas is expanding and doing positive work. If we're going the other way, it would be negative 2,000 joules. Work would be being done on the gas, but since the gas is expanding, the gas is doing work. And so these are our two values. Well, three if you want to count Q equals 0.